Before we get started into actual physics, we need to know the difference between a vector quantity and a scalar quantity because we're going to be using vectors quite a bit. So let's go ahead and define what a vector is. A vector has a thing called a magnitude, and that's synonymous with the word size, right? So something can be large or small, but typically we use a number to be able to designate that. So it could be 10 meters or 50 newtons. The other aspect of a vector is that it has a direction. And that direction is in degrees. So you'll want to set your mode on your calculator to degrees. And we usually use the marker of the positive x-axis or the compass. So we'll talk about some of those examples as we go. So a vector has both a magnitude, forgot the E there, both a magnitude and a direction. A scalar quantity only has a magnitude. So it exists or it doesn't. It doesn't matter what direction it's going. So if someone were to say to you that two lions escaped from their cage at the zoo and you happen to be visiting that zoo, you definitely want more than just the scalar quantity. You want to know what direction they're going so that you know whether or not you need to run. All right, let's take a look at examples of vectors. So displacement. And displacement, I'm going to put a little note here as the crow flies. So it's not really following the path. It's from point A to point B, the straightest line. So we'll talk about that more. Velocity is a vector. Acceleration is a vector. Force is a vector. Momentum. And again, you can pause this video at the end here and then write all this down. And then, of course, gravitational field. Direction does matter. So those are the big hitters for what we're going to be studying this particular year. And then we'll contrast that with scalar quantities. Scalar quantities are just a value. So distance is actually a scalar quantity. So think of that as your odometer in your car. So it just tells you how far you've gone, how many miles you've driven. Speed is also just a scalar quantity. It's only telling you how fast you go. So that would be this similar to your speedometer. Mass is a scalar quantity. Energy, you either have it or you don't. Energy. Temperature. That's another scalar quantity. And time. Now, time is a little bit controversial because there is a dimension to it, but we are not going to be time traveling in this class. So we're going to consider time always moving forward. So that will be a scalar quantity for us. All right, let's take a look at some vocab and attributes. So one thing that we need to understand is with a vector, it can have movement. So let's say I draw a vector right here. Okay, I can take that vector if I want and I can move it. Let me get rid of the top here. I can take this vector and I can move it anywhere I want to on a coordinate plane. Oops. It could be here, it could be here, it could be there, it could be here. So I can move it anywhere I want, but it has to stay that same magnitude and that same direction. So I can't change those. So we can move, oops, make it thinner here, move on coordinate plane, but must have same magnitude. I'm just going to abbreviate it here, and direction. Okay, so you can't change that, but you can put it different places within that coordinate axis. Remember, the coordinate axis is just a frame of reference for us, and we can define our own frame of reference. Magnitude is going to be the size of the vector. And the vector that we designate is going to be a line with an arrow. And when we look at that vector, we have a part that's called the tail. And then this is called the tip. So when we add vectors and we use the tip to tail method, that's what we mean. And then the direction, the magnitude, it has a unit. So we could say, for example, 10 meters, 50 newtons, -3 meters per second. Now, this negative thing here actually speaks to our direction, okay? So let's look at what we mean by direction. Typically, this is done in degrees to the x-axis, the positive x-axis, or we can use north, south, east, and west as a designation. And if you have just a negative, then it denotes on the negative x-axis or the negative y-axis. So we'll just have to be very careful with this. When we talk about vectors, we definitely want to do a angle, but sometimes as we get into our forces and our velocities, you'll see where we can change that a bit. All right, denoting a vector. When we write down a vector, typically we write it in brackets. So just like we would a coordinate. So let's look at this particular one right here. Okay, do you see where it's 2, 3? You can also write it that way as well. As long as your tail is at the origin, you can use the standard coordinate for it. If this was shifted a little bit over to the right, you could still have 2, 3 designated. You would just have to recognize that that's not where it lands on your coordinate axis. So you could have 2, 3 to denote your vector. And of course, I'm talking about this vector that's right here. When I have that, you'll see that it's 2 on the x-axis and then 3 on my y-axis. So I'm really creating a triangle. That's all we're doing when we look at the components of a vector and then determining what the value of a vector is. But the components, we use I, J, and K. It's very common to have this in pre-calculus coursework, but you may have skipped it if your particular instructor didn't feel that this was a critical standard, which is fine. You're going to learn it here. So when I look at the I, the designation of I, I'm talking about the x-axis component. Okay, so in this example, this is my x-axis. Hang on a second. This is not writing really well. Axis component. So in this way, I would say 2i. Get the I a little bit better. There we go. Okay, so that would be 2i. And then j is going to be my y-axis component. And k is going to be my z-axis component. We're going to go ahead and talk about that. You will not be responsible for finding the direction of a z-axis, but we can, we'll definitely find the magnitude. All right, so I, J, and K. Here we have our y-axis, and then our z-axis would be coming in or out of the page. So if that's 2i, then this would be plus 3j. So that's how we would designate that particular vector. You can use V to symbolize a vector. R is very, very common because we use it to signify a resultant vector. All right, so let's go ahead and take a look at this example. We've got a vector here, and I've given you the terms. Let's say our units are meters, okay, just so we don't have any naked numbers. So if I want to put this in component form, that vector would be 4i plus 3j. So using my x and my y axis, that's what I've got. Okay, and again, I'm using this information to kind of fill in the blank. Well, how do I find out what this r is? Take a look at that triangle. How would you solve it if this was geometry class? Absolutely. We would use the Pythagorean theorem. And that's how we are going to get our components into an actual vector. So the way that we write that, remember it's a squared plus b squared equals c squared. That's the Pythagorean theorem. If we're solving for c squared, we're going to take the square root of both values, right? And then we end up getting just c for our answer. Well, this is how we would write it. So it would be the absolute value of r, because we just want the magnitude, is equal to my x component, which is 4, and I'm going to square that quantity, plus my y component, which is 3, and I'm going to square that quantity. So my r is equal to the square root of 16 plus 9, which is the square root of 25. So my vector quantity is 5. And again, we said it was meters. Now, hopefully you recognized that I had a 3, 4, 5 triangle. So your Pythagorean triples, is something that you definitely want to make sure that you understand what those are. What we can do in class is list what those Pythagorean triples are so that you get used to using those. All right. Well, how do we figure out this angle? Well, this is where that B and that A come back in. Okay, so we're going to use some of our trig knowledge. So to find that angle, I know my y value and I know my x value. So in this case, I know that the tangent of that angle is going to be the opposite, which is my y, over my adjacent, which is my x. So this is going to be pretty standard. As long as your angle is with respect to the positive x-axis, you're going to have the setup just like this each time. So how do we solve for theta? We got to take away that tangent, which would be the inverse tangent. So the inverse tangent of y over x. So let's go ahead and put that into numbers. My angle is going to be the inverse tangent or the arctan. You might, on Desmos, you have to type arctan, A-C-R-T-A-N. So the arctangent of my y value is 3 and my x value is 4. And when I do the math on that, I end up with 36.870 degrees. Notice that I'm carrying it to 3 decimal places. When you are in calculus, you're supposed to keep all of your answers to at least 3 decimal places. You can truncate it or you can round, it doesn't matter. I like to keep the physics in that same realm. As of just prior to the new iteration, it did not require significant digits. So I will double check on that just to make sure that you're in good shape. All right, so let's go ahead and shift to the page here, and we're going to do an example. So find the magnitude and direction, which is the angle you're finding, of the vector 6i minus 3j. So I'm going to go ahead and have you pause it right here and then we'll go through that to check your answer. All right, let's go ahead and draw our vector. So we want 1, 2, 3, 4, 5, 6 going that direction, and 3 going this direction. So that gives us our vectors, components, and then my actual vector is going to be this red line. Notice it's in the fourth quadrant, right? Just so you remember your 4 quadrants. And with those 4 quadrants, we're going to designate it with respect to the positive x-axis. So ultimately, we will find this angle, but I can also talk about it being south of east. All right, let's go ahead and put it together. My resultant vector is the square root of 6 squared plus negative 3 squared. So that gives me the square root of 36 plus 9, which is the square root of 45. And that's going to approximate about 6.708. My angle, I know the tangent of my angle is going to equal my y value, which is negative 3, over my x value, which is 6. And so I've got my angle is equal to the inverse tangent of negative 3 over 6. And I'm going to actually get a negative number. That negative number is going to be negative 26.565 degrees. So that tells me that it's 26.565 degrees below the x-axis. So I could say 26.565 degrees south of east. That would be one way I could write it. Or I could say, I could add 360 degrees to that, and that would give me the value of 333.435 degrees. So I could do either way as my answer. Okay, so we're looking for this answer and we're looking for that as our angle. All right, let's look at number 2. A bicyclist travels due west 5 kilometers and then turns south and rides 5 kilometers. What is the distance the bicyclist traveled? And what is the displacement of the bicyclist, excuse me. So go ahead and pause this video and work on this and see if you can go ahead and solve for your displacement vector and your angle. And then keep in mind too that you've got a new term here, which is the distance. That's a scalar quantity. So see if you can figure that one out. All right, let's go ahead and take a look together. I've got 5 kilometers west, so 1, 2, 3, 4, 5. And then I've got 8 south, so 1, 2, 3, 4, 5, 6, 7, 8. So my vector quantity is going to be this right here. So the answer that I get is going to be south of west, right? If I'm looking for this particular angle, or I would find the angle all the way from the positive x-axis. All right, let's go ahead and work on this. My vector is equal to, well, before we do the vector, let's talk about the distance, right? My distance is just like my odometer. So if I was looking at my odometer in this, that would just be my 5 kilometers plus my 8 kilometers, right? So 5 plus 8 is going to give me 13 kilometers. So that would be my distance. My displacement is going to be my vector as the crow flies, right? So this right here is as the crow flies, whereas my distance was the route that I took. So that vector is going to be the square root of -5 kilometers squared plus -8 kilometers squared. So I have square root of 25 plus 64, and that's going to be the square root of 89. So the square root of 89 is going to be approximately 9.434, and that's going to be kilometers. It should be larger than your longest edge, right? So just typical geometry. So that 8 kilometers, it should be larger than that. It should not be larger than the addition of both sides. So we're underneath that 13 kilometers. We're in good shape. Okay, so then the next part that we're going to do is find our angle. And our angle is going to be the inverse tangent of my y value, which is -8, over my x value, which is -5. So if I take my 8 divided by 5 and do the inverse tangent. Okay. I apologize, guys. I ended up not doing this one on my calculator already, so I've got to do it on my calculator right now. So inverse tangent of that is going to give me 57.995 degrees. Now, where is that located? That's on the inside. So in that third quadrant, that's the full 180 that's here plus that 57,995. So if I add 180 to that, so plus 180, it's going to give me 237.995 degrees. All right, so that is our vectors and looking at components and coming up with our vector from our component. It's quite a bit for the first time. And then on Thursday, we will look at part B, which is the addition of vectors, and we'll probably even include part C, which is subtraction. It's the same as addition, it's just moving at 180.